All right, it is 9 a.m. on the dot, so we're going to get started with this morning's field trip. Welcome, sixth graders, to the Dallas Independence STEM Environmental Education Center. We would like to welcome 4 schools that have registered for today's field trip. The first one is Griner Middle School. Welcome, students from Griner. The next is Reagan Middle School from Grand Prairie ISD. Welcome. The next school is Rosemont Elementary, so welcome, sixth graders from Rosemont. And last but not least, we have Jose Jomay, sixth graders from Jomay Elementary. Thank you so much for registering for today's field trip. If you are watching this and have not registered yet, you can still register for today's field trip. And how you do that is by going to www.tiny.cc/EEC register. And there you can get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And today's field trip is called Force and Motion Are Related to Potential and Kinetic Energy. During this virtual field trip, students will discover that force and motion are related to potential and kinetic energy. Students will compare and contrast potential and kinetic energy and describe the changes in position, direction, and speed of an object when acted upon by unbalanced forces. So we're going to start off this morning by exploring potential energy. Then we will explore kinetic energy. Next, we will explore changes in position, direction, and speed. And last, we're going to look at net force, Newton's laws, and vectors. While we're doing all of that, you can ask us questions. How you do that is by going to www.tiny.cc/EEC-question-answer. And once you get there, you can ask us any question you have related to potential energy, kinetic energy, speed, motion, everything we're doing today. You can ask as many questions as you like, and we will do our best to answer all of them for you in the time that we have with you this morning. So I'm going to stop sharing my screen here and pass it off to Ms. Nash, who's going to get us started with potential energy.
Good morning. Welcome to my class. Today we're talking about potential energy. You may have heard someone say you have a lot of potential, and I'm sure you do. That means you can do great things. So potential energy is stored energy that can be released in different ways. So the first thing to think about is plants, because I'm sure you had breakfast already today. And when you ate your breakfast, what you're consuming is stored energy, chemical energy in that fruit. Plants store that energy through photosynthesis, sun, air, and water, right? And they use that potential, that stored energy to grow, and then we animals eat them. And then we have also stored chemical energy. And that's how we can get up and move around and read and think and do all kinds of fun things. Another thing to think about, like I have 2 little objects here. And actually this one's a lot heavier than this one. My little clementine and a little muffin. Now, which one do you think has more chemical energy in it? In other words, calories. So this one has 36 calories, more or less, and this one has 100. Even though it's smaller, it's more chemically dense. Okay? So don't eat too many of these. You eat more of these. You don't want to get fat. So that's chemical energy, and that's what we're using all the time. It's stored in our cells. We eat our food, we store the energy, and then we can move around. Now, there are other kinds of potential energy. The fun one to experiment with is gravitational. Now, because gravity pulls things to the earth, depending on everything that has mass has gravity. And the amount of mass determines the amount of gravitational force. So our earth has a lot of mass, so things fall down. That's all it's right. But you can make little ramps like this one, and then we can make some tests. And I can take 2 little balls here. This one's bigger, and this one's smaller. Smaller, really small. But this one is a lot lighter. So if I put them on the ramp, same time, I put them on the ramp at the same time. What do you predict is going to happen? Who's going to win our little race? Let's see. There we go. So this one won the race because it has more mass than this one, right? Now if I take 2 of the same ones and I alter the height have my ramp. What do you think's going to happen now? Who do you think's going to win? What do you think? Really? Okay. So clearly, being higher up increased the amount of gravitational energy, potential energy that ball had when it was up there. And this is a really fun thing to do. You can make your own ramp. Okay. I made this one just with paper towel tubes that I cut in half. I taped them together, and these are good for balls. Okay, if you have a little car, it won't work very well. But this is great for testing out different kinds of balls. It's really kind of fun to test and see which ones will win the race, okay, depending on their position and the amount of mass. The amount of mass they have. So the gravitational energy depends on how high they are above the Earth or whatever you can fall onto, and also the mass of the object. So we, clever people, figured out a lot of ways to use potential energy. So I made myself a little spring. I just wrapped wire around a little tube like that, and I made a spring. And then if I compress it, it can pop up and throw things around. Okay, it can be really useful. But I'm storing that potential energy in the spring. Another kind of potential energy that we're familiar with, and it's also fun to test and play with, are rubber bands. Okay, so you can pull them, and then now they've got stored energy, and then they come back. Don't throw them at your friend. Don't hurt them. Now, another thing that we're really familiar with are batteries. So batteries are just stored chemical energy in here. Okay. And I can use that battery to turn my light on, so it'll work for me here. Maybe not. Oh, the batteries may be dead. Uh-oh. Okay. I can also store energy in this flashlight. It doesn't have any batteries, but it still works because I've stored a different kind of energy in here. Just by moving the little thing, I'm storing energy. It works pretty well. I don't need batteries, which are toxic. We should avoid them if we can. Here's another fun thing to think about. Now, so I pull it up here. Now it has potential energy. So if I let it go, up here it has the most potential energy. Now if I take two of them, am I going to have more potential energy? Let's see. Take two. And it'll gradually stop because of friction. Because each little bit of energy is lost each time. But it's a pretty interesting thing to try because the potential energy is up here. I've got, if I put it up higher, what do you think will happen? It's going to go up higher. If I don't have quite as much potential energy, less effect. So a pretty interesting demonstration. So you can think about you can make little toys to demonstrate potential energy. My little froggy here, see if I make him jump. He's got potential energy and he jumps. Okay. Now, when we go camping, we take these little cans with us, and inside, I can hear there's a liquefied gas inside, isobutane propane, and it becomes a gas, and then I can turn it on, and I can light it with a match, and I can cook my food. The interesting thing is that when we go camping, backpacking up in the mountains, it's cold at night. If you leave this outside your tent in the morning, it won't work. So we have to take this in the tent and keep it in there with us to have it be warm enough to become a gas, and then we can cook with it. But this is the way gasoline works in your car. It's a liquid and it comes out of the pump, but then it becomes a gas. So this is stored energy right in here. Lots of it. So, boys and girls, there's lots of things to do and discover I think it's fun to experiment with some ramps. Okay, what different things, different kinds of balls, how high, how low, what kind of changes can you make? And then go around your house and make a list of all the sources of potential energy that you can find in your house or in your classroom. So if you have any questions, and have a good day, nice rainy day out there. But if you have any questions, Mr. Broughton will answer.
Thank you, Ms. Nash. The question that came in was, what was that thing called with the marbles hanging from the strings? And that is called Newton's Cradle. It is named after Sir Isaac Newton. We're going to learn more about Isaac Newton when we get to Newton's laws at the end of today's field trip. And that device demonstrates conservation of a momentum and demonstrates energy. So we're definitely learning about energy today with potential and kinetic energy. Conservation of momentum is probably something you will learn about when you take physics in high school or in the 8th grade, depending on what track you're on in science. One other thing I'll mention is you maybe noticed that those marbles don't swing forever, and that is because while they do conserve energy by being so close to each other, they do lose some energy in the form of sound. You can hear them clicking. So every time they lose a little bit of energy through sound, they're not going to be able to swing quite as far. All right, now we're going to move on to potential energy with Mr. Ramirez. Kinetic energy, I'm sorry, with Mr. Ramirez.
Hello, my name is Mr. Ramirez, and in this segment, we're going to be looking at kinetic energy. So earlier with Ms. Nash, you learned that potential energy is just the energy an object has due to its position. Kinetic energy is actually the energy of motion. And generally, kinetic energy will increase as mass and speed also increases as well. So kinetic energy is just energy of motion, and it is related to a theory called the kinetic theory of matter. And essentially what that means is all states of matter are made out of particles, and those particles are always in motion. So as we increase temperature, the particle motion will also increase. So states of matter, whether it's a solid, liquid, or gas, they're all made out of particles. And solids, those particles are going to be moving very slowly. They're kind of vibrating and rotating in place. Liquids, those particles are moving a little bit more faster. They're able to slide past each other. And then when it comes to gases, those particles are moving the fastest out of all the states of matter, and they're able to move more freely. So the kinetic theory of matter is just stating that all matter is made out of particles that are always in motion, and that is how we get our different states. So what we're going to do first, we're going to look at a quick little video of examples of kinetic energy here at the Environmental Center, and I'll be discussing how they represent examples. So let me present my screen with you guys. The first video we're going to take a look at is of a windmill and a couple of some other live animals that are found out here. And as you're watching the video, be thinking about how do you see motion being represented. So here's our windmill. It's converting the kinetic energy of that moving wind into mechanical energy. So there's a gearbox at the top of the windmill, and it's causing that pump that you see there to pump water from underground into our pond, and we can also use it to water our animal troughs. So there's a pipe that goes from the windmill to our pond, and you can see water's being pumped into that pond. Unfortunately, it doesn't look like the best pond right now. We've had some period of drought, so we don't have a lot of water left. But you can definitely see all the animal footprints. That's our little donkey. You can see the water trough over here. So again, we do use underground water to help water and provide water to our animals. This one is a spider. The spider is moving, so he's using mechanical energy to carry out everyday functions. But also the web has to be strong enough and arranged in such a way to stop and absorb the kinetic energy of flying insects that hit his web. And then I have one last video. As you learned earlier with Miss Nash, our animals are constantly converting food energy into chemical energy, which we then use to help power our everyday motions that we do in life. So here are some ducks. So everyday animals transform the chemical energy held in our food into mechanical and thermal energy. And we're using that energy to carry out our everyday processes. So that might be walking, eating. In this case, they're quacking. So noises are an example of sound energy, and sound energy is actually also an example of kinetic energy. So I'm going to go ahead and stop sharing our screen, and we're going to look at a couple more examples of kinetic energy. So those were examples of kinetic energy out here. Now we're going to look at some examples of kinetic energy that might be more familiar to you guys involving some toys. So kinetic energy is found in several different forms. It can be radiant energy. Radiant energy would be things like electromagnetic waves, and that would be evident in things like light and solar energy. Another example of kinetic energy would be thermal energy. So thermal energy is just the vibration and movement of particles within substances. Another example of kinetic energy would be sound. So we hear sound because it's the movement of energy through a medium. And then also electrical energy. Electrical energy is just the movement of electrons. Examples of that would be things like electricity and lightning. So as I show you these toys, be thinking about what forms of kinetic energy are evident in these toys. So let me go ahead and slide our box over and change my camera view just a little bit. So the first example of our kinetic energy, and we're also going to be talking just a little bit about potential energy because they're sort of tied together. So here we have a spring-loaded car. Y'all saw springs earlier with Ms. Nash. The spring is the potential energy part, and when I release the button, the spring will uncoil, and when the car moves, that would be the conversion of potential energy into kinetic energy. So that's the kinetic energy part, the motion part. Here's another example with a spring-loaded car. Again, the movement would be kinetic energy. Here is our wind-up toy. I am winding it up. I'm storing that elastic potential energy. And when I release it, it's going to be converted into kinetic energy, the energy of motion. Another example, we call these mechanical sharpeners or mechanical pencils because we actually have to do work. We have to exert kinetic energy to make it work. So for example, I have to actually move and use mechanical energy to make the mechanical work. The same thing with the mechanical pencil. I have to move and exert energy to release the lead so that I can write. Something similar that Ms. Nash showed you guys, this is a flashlight. I have to exert mechanical energy in order to convert that mechanical energy into a form of energy that can release this light to make the flashlight work. Here's another toy. I'm going to press the buttons, and you're going to see multiple forms of energy being demonstrated here. Oops. So theoretically, if it were to work right, the string would swirl all the way around, and you would see there you go. So we have kinetic energy with the motion, the swirling of the string. We also have sound energy, so we can hear the sound, and we also have light energy as well. So things can have multiple forms of energy being demonstrated. And then we talked about sound energy. So again, sound energy is just the vibration of particles within a medium. So if I touch these, you can hear a sound, but also because I'm able to hold these, I can actually feel the vibrations. So this is an example of kinetic energy, sound. Also, here's a dried okra. I can shake it, and you can hear the sound being released as well. So the next thing we're going to take a look at is another form of energy. And if we take a look at this lava lamp, I forgot my oven mitts today. I'm going to hold it with this. This lava lamp is converting electrical energy. So electrical energy is another form of kinetic energy. So again, electrical energy is just the movement of electrons. And so we are using this electrical energy. It's converting it to heat energy. So there's a bulb inside, and that bulb is heating the fluid inside this lava lamp. So you can see movement. That's the kinetic energy, the movement of the fluid inside. And the way the lava lamp works, when things get heated, so for example, this blob here, it got heated. And when things get heated, they tend to rise because they become less dense. When they rise to the top, they are further away from the heat source, so they're going to start to cool. When things cool, they will start to sink because they become more dense, and they will sink to the bottom. And then the whole cycle will start all over again. So that heating and cooling of the fluids is known as convection. And that's a form of heat transfer. So again, heat and thermal energy is an example of kinetic energy. And then just the last thing to wrap up remember we were talking about the kinetic theory of matter. So to demonstrate the kinetic theory of matter, remember all things are made out of particles. So for example, here I have a little container. We're going to say that these beads represent the particles that make up matter. If I just shake it a little bit, the beads are kind of just moving very slowly. So they have very little kinetic energy. So this might represent a solid. Now, if I were to add more energy to it, you can see the beads start to move more rapidly and more freely. So this one has more kinetic energy than our first try. So this might represent the phase of a liquid. They're able to flow more easily. Now, if I add even more kinetic energy, more movement, you can see the particles are able to move more rapidly and more freely. So this might represent the particles of a gas. So be thinking about the things that you see in your everyday life, whether they are liquids like this popsicle, whether they are solids like this rock, or whether it's gases like the air trapped inside this container. Be thinking about how those particles are moving. So think about the kinetic energy within those items. And then the last thing for you guys, I just have a little quick challenge question for you guys. I have a little demonstration I set up, and we're going to take a look at it. And I would like for you guys to be thinking about what examples of energy are evident in this demonstration here. So I have 3 candles. On the top of one candle, there's a spinning rod with these little spinning snowflakes. So what examples of energy are evident in this spinning candle demonstration? So think about the forms of energy that I talked about. Think about the ones Ms. Nash talked about. What forms of energy do you see here in this example? And also think about what is causing this top to spin. And that's all I have for you guys today for kinetic energy. We're going to go ahead and pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. The question that came in was, how is kinetic energy related to potential energy? And remember, potential energy is energy stored in an object due to its position or arrangement. And then kinetic energy is energy of an object due to its movement or its motion. So if you could imagine, like if I were holding a spring here, if it was really easy for me to compress that spring, it's probably not going to have a lot of potential energy because it was easy to compress. So if I let it go, it's going to push something, but not very hard. So when that movement starts, it's also not going to have a lot of kinetic energy. But if I had to really, really use all my strength to compress a spring, if I were to let it go, it would shoot off that object even more. So more potential energy usually equals more kinetic energy. Same thing in a battery. If you have lots of energy stored in a battery, it's going to be able to do more things for you. If there's only a little bit of energy left in a battery, you're not going to be able to do many things with that. All right, now we are going to move on to, let me take a look here, Mr. Monroe, and he is going to explain changes in motion, direction, and speed.
Okay, good morning, students. My part of your virtual field trip today is to deal with the changes in position, direction, and speed of an object that is being acted upon by an unbalanced force. And basically, I'm going to be using a magnet today in today's investigation simply because when we talk about force, we're talking about the push or pull. And, you know, it does have an effect on certain objects as far as them moving at a certain speed and moving in a certain direction and even coming to a stop that defies another unbalanced force that we call gravity. Now, let me explain something about a magnet. Now, a magnet is not going to interact or not going to put an unbalanced force upon certain types of matter. Basically, the types of matter that magnet is going to have an effect on are, it's going to be objects that are made up of matter that has a certain amount of iron metal in that makeup of that matter. So, first of all, let's get the basic understanding about a magnet. The strongest pull that a magnet has is at its poles. We know that a magnet has a north pole and a south pole. The strongest point would be at the end of this bar magnet or at the top of this bar magnet where an S for the south and an N for the north is located. On a horseshoe magnet, it would be the same thing. Where the S is located, that's the south pole. The N is the north pole, and that's where the strongest pull and push is located. And what I mean by push, we know that like poles repel each other, and unlike poles, they attract each other. For example, this two magnets here, we see that I've got the two south poles trying to face each other, and they're actually pushing away. So there's a change in direction is exemplified right here. When I change this and put the north pole to the south pole, they will attract and draw themselves together. Now we know that gravity works on objects, regardless of what they're made out of. If gravity wasn't present, then basically everything would be floating around. We know that. I've got a string of beads right here. It's almost like a pendulum. And if I swing it back and forth and I pick up a magnet, can I change the motion of this string of beads? Yes, I can bring it to a stop because I have now pulled the string of beads over to the magnet. So the magnet is acting as an unbalanced force. Can I change the direction? Can I make? Yes, we can change the direction. It's not swinging back and forth. It's spinning. It's spinning now. Now, what about this ring magnet that I have set up on a pedestal? We know that gravity pulls everything down, right? If I was to drop this ring on top of the pedestal, it would slide down the rod as gravity pulled it down. When I try to pull this one down or try to get this one to go down, we're going to see that it doesn't go down. And that's because, again, there's an unbalanced force acting upon this ring. And I can tell you right now, this was a magnet. And this magnet probably has a like pole that's working against the like pole or repelling that like pole on this ring magnet. As far as affecting direction, you know, magnets are a big part of an instrument that we use today to find our direction. And everyone knows that if you were out in a place where you couldn't find your direction, didn't know which way to go, you considered yourself lost, it would be good for you to have an instrument called a compass. And that compass basically would help you find your direction. Now, one of the reasons that I picked the magnet to do this demonstration with is the fact that our planet, the planet Earth, is considered to be acting like a big magnet. Of course, we got the gravitational pull, but we know that the top part of our planet, we refer to that part of the planet as the North Pole. The bottom part of the planet, we refer to that being called the South Pole. And there is a bit of magnetism that goes on between the two. In fact, often we refer to the North Pole as the magnetic north. Now, students, I have created a homemade compass here. And what I have suspended on a string is a magnet. Now, that magnet is moving right now. It's spinning. Now, I can tell you it's going to change its direction, changing its direction because there is an unbalanced force working on this magnet. It's going to eventually point toward the magnetic north. Okay? It's spinning. It reversed its spin. Did you notice that? It's spinning. Going to settle in now. Now, in this lab, I know the direction of north from my lab here. And I can tell you magnetic north from this lab right here is that direction. And I can see that eventually this is going to settle in and it's going to give me the north direction. Now, to really prove that this is being enacted on by an unbalanced force, I have a real compass here. And I'm looking at this compass, and it's lining up with this magnet right here, pointing that that is the north, okay? Now, another thing that I'd like to mention is that many, many years ago, one of my favorite things, I guess this is when I was in junior high. They called it junior high back then. Today they call it middle school. But when I was in junior high, one of my favorite places was to go. There was kind of like this hangout place. And at this hangout place, there were these machines called pinball machines. And inside that pinball machine, there were these big steel balls like this. And you would put a coin in, and I think it would give you about 5 of these balls to work. The ball would come from the top, and it would be on an incline or decline, and as it was rolling down, you had certain things that you could do to keep that ball up there hitting some of the objects on in the pinball machine, and you would score points that way. And there were flippers that you could flip to make, if you hit the ball, it would go back up. And sometimes I wondered what in the world was going on with that, because sometimes that ball did things on its own. I mean, without me flipping it, it would change direction on me real quick. Well, it wasn't until later on I found out that embedded in the scheme of that pinball machine, there were magnets. And because steel has a little bit of iron in it, what we had was a lot of unbalanced forces going on. One was dealing with the gravity, because the actual playing area for the ball to come down was on a decline or an incline slope, and it was rolling quite fast. And then once you hit it with a flipper, it would send the ball back up, and you could score more points. Every once in a while, that ball would take a exit to the side, and you didn't have a chance to use your flippers. It was kind of chaotic, and I've got some steel ball bearings here that I'm going to pour inside, and we're going to get them to kind of mix up a little bit, turn around. Let's see if a magnet would have any kind of effect. Hopefully you guys can see this. Well, that magnet is not quite strong enough. Let's see if we can get another one to be strong. It's not strong enough. But that's the way it would work, guys. Those balls would be rolling all kind of crazy around, and just no logic to it. No logic to it. They'd be all over the place. And I was trying to score points with those balls and just could not understand what was influencing those steel ball bearings. And that was a perfect example of a lot of different unbalanced forces acting upon those objects. Hopefully I've given you a little information about the push and pull that unbalanced forces can have on objects by using a magnet. And if Mr. Barton is there, he might be able to answer some of those questions that you might have for him. And I'm going to turn it back over to him at this point.
Thank you, Mr. Monroe. The question that came up was, how does gravity change the direction or speed of an object? And I think I have come up with a good example of that. This is a little picture that talks about gravity assist. So sometimes in NASA, we'll use gravity assist to fly spacecraft. So if you look at this, let's just look at the black lines first. This is the moon's orbit around Earth. So the moon is moving that way. This black line is saying which direction Earth is. So if you were on the moon and needed to get back to Earth, you would go this way. And then from Earth, we send spacecraft out into space. But sometimes we use the moon's gravity to help us make that spacecraft go a certain direction or a certain speed. So if we wanted it to go faster, we could start it off from Earth on this red line, and it's going to leave Earth's gravity and enter the moon's gravitational pull, where it's going to be much more affected by the moon, and that gravity is going to start to pull it in, but it actually makes it past and shoots it past the moon that way. So it's called the slingshot, and it's accelerated by the moon because since the moon is going this way, the moon's going to kind of pull that spacecraft along and help it speed up and go that way. But let's say we didn't want to go left, we wanted to go right. You could shoot it past this side of the moon, and then the moon's gravity is going to pull it around this way, but it's also going to be decelerated by the moon because since the moon is going this way and your spacecraft is going the opposite way, the moon's gravity is going to slow it down. So even in space, we can use unbalanced forces to change the speed or direction or both of objects that we send out into space. All right, now we are going to move on to Mrs. Fuller with Newton's laws.
Good morning, boys and girls. Today we're going to be talking about the 3 laws of motion that were discovered by Sir Isaac Newton. Now, Sir Isaac Newton was an Englishman. He's considered probably the second smartest person who's ever lived after Leonardo da Vinci. During the Black Plague, this plague is not the only plague we've ever had, not the only pandemic, and he was sent to the countryside to live because it was too dangerous to be at university. And he discovered the law of gravity during that time. So even though we're sort of on lockdown, we can still do plenty really big things. Now, a few years later, in 1786, he wrote a book called Principia Mathematica, and in it he laid out 3 laws of motion. And the first law of motion is an object at rest will stay at rest unless acted upon by a net outside force, and an object in motion will tend to stay in motion at the same velocity and in the same direction unless acted upon by a net outside force. His second one is the vector or sum of the forces, F, on an object is equal to mass times acceleration. And his third law says for every action, I know you've heard this one before, for every action there's an equal but opposite reaction. So we're going to start off by talking about inertia. Inertia comes from the Latin word which means laziness or idleness, and essentially what it means is not doing anything, at rest. So we're going to demonstrate, let me talk a little bit about vectors and net force, then I'm going to demonstrate some inertia concepts here. Now, a vector or a force is a vector, and 2 forces of equal magnitude and opposite direction will cancel each other out. And we're going to demonstrate that in just a minute. Now, net force. What's net force? Net force is defined as the sum of all the forces acting on the object. And net force can accelerate a mass. So we're about to demonstrate that. And you say, well, what are forces? Well, those are things like gravity, wind, friction. Mr. Monroe just demonstrated magnetism to you, even the mechanical energy of my hand. So let's look at that. So we're going to start off with a real simple demonstration. Here is a coin. It's a quarter. It's on top of a card on top of a beaker. I'm going to remove the card very quickly, and because the quarter is not going to be acted upon with a net force, it's going to stay the same. Well, when I remove the card, it's going to fall into the beaker. So here we go, and let's hope this works. It didn't. Let me try one more time. Okay, here we go. There we go. So it worked that time. So what happened was we removed the card quickly, and the coin, because it did not have a net force acting on it, stayed the same, and then gravity pulled it down. So there's one example. This one right here is kind of messy. We might wait till the end to do this one. Now this is an inertia hat. It's very simple. You can make one out of a clothes hanger and just stick two tennis balls, or in this case, I put two globes on the end. So as you can tell, I'm not moving. So an object at rest tends to stay at rest unless acted upon by a net outside force, where there are no forces that are together that are causing it to change direction or to move. But I'm going to push it with my hand. The mechanical energy in my hand is going to cause it to spin, and it will continue spinning until acted upon by a net outside force. In this case, you see it came to a stop. It came to the stop because of the gravity of my hair. My hair, not the gravity of my hair, the friction of my hair. My hair slowed it down. So that was the net outside force. Now you say, well, it could be any force. Well, it has to be a net force to overcome the mass and the acceleration of it. So in other words, I can touch both of them like this. It's balanced force. So nothing's happening. It's when I push on it and it overcomes that. It's unbalanced, and that's what caused it. Mr. Monroe talked about that with you a few minutes ago with the magnetism part. Now, before we get to our other inertia experiment that's messy, we're gonna, this is his second law, force equals mass times acceleration. And I just demonstrated that with the inertia hat. Let's talk about the third law, Newton's third law, which is for every action, there's an equal but opposite reaction. Here's a real simple one. Okay, here's a book. It's an oceanography book. I'm putting it on the table. The book is exerting a force down because of gravity, but the table is exerting a force up to support it, so they are balanced. So they are equal but opposite, and because of that, the book is not moving. Another one that you probably experienced yourself, if you've ever gone to the lake and you've tried to get into or out of a boat, sometimes if you have one foot on the pier and the other foot still in the boat, when you push with your foot to get up on the pier, the boat moves away from you and you may have even fallen in the water. That's equal but opposite. That's the third law. So let's go back to our inertia experiment. And I've done this both successfully and unsuccessfully. So we'll see which one it turns out. We've got a pickle barrel of water. We've got a pie pan with a toilet paper roll and a box with a fossil in it. So it's all stacked up. So in theory, if I can very quickly remove the pie pan and the toilet paper tube, the box with the fossil will fall into the pickle jar. Now, we're going to try it, so here we go. And it worked. Yay. So science in action. So have a great day. I'll turn it over to Mr. Broughton. Thank you.
Thank you, Mrs. Fuller. That was great. All right, now we're going to do a quick recap of what we did today. I was holding my breath there watching that fossil box fall in the water. Today we explored that force and motion are related to potential and kinetic energy. So during this virtual field trip, students discovered that force and motion are related to potential and kinetic energy. Students compared and contrasted potential and kinetic energy and described the changes in position, direction, and speed of an object when acted upon by unbalanced forces. So remember, if something's moving, the forces are unbalanced. If it's not moving, the forces are balanced. We started off by exploring potential energy with Ms. Nash, then kinetic energy with Mr. Ramirez, Then Mr. Monroe explained changes in position, direction, and speed. I'm using magnets and pinball machines. I still play a pinball machine at a car wash where I go to get my truck washed. And last, Mrs. Fuller explored net force, Newton's laws, and vectors. Thank you so much for joining us this morning. We appreciate you taking the time to explore forces with us and how they change speed, direction of objects. We'd like to know what you thought about today's field trip, and you can let us know by going to www.tiny.cc/EEC feedback and filling out a short form. It takes 1 or only 2 minutes at the most to fill out to let you know what you thought about today's field trip. We use that information to improve what we do here, and hopefully we'll see you again in about 3 weeks. Have a great day. Goodbye.